Well, this is our second video looking at matter and motion. And the classification of matter you've heard probably from grade school is still fitting. We have two really important buckets or divisions that we place matter into, whatever we touch. It'd be this coffee cup or my hand or this marker I'm about to use. It's either a substance we're touching pure, and it's pure in one of two ways we'll see, or it's a mixture. And most of the things we touch, complex machines, phones, they're made with different phases coming together, parts that can be distinguished from each other. That's a mixture. So if you look at the picture here, there's really two types of mixtures we can have. Those that the eye can distinguish as being different. So your eye can see, for example, as I drink this cup of coffee, there's coffee in there, and it's not part of the ceramic cup. This would be, if we consider the whole, a heterogeneous mixture, both of a solid and a liquid, but they're different in not just their elemental composition, their coffee, and it's ceramic, but also in their phases. But we can also have in the coffee, I'm just going to come back to it, we dive into the coffee and I'm inside the coffee and I consider just that area in the middle of my coffee cup. I'm looking all around and everything would be the same to the eye. But inside, we know that coffee has, of course, water. So we could say that some of this would be H2O that we're looking at, or Miss Frizzle took us out down on her bus and we're able to see things at that level. We'd see water. And then we might see, of course, caffeine. And you're going to see some tannins and parts of the mixture at the compound level, chemical level, that makes coffee. That would be a homogeneous mixture. There's no part of this, as you look at it, looks any different from another. Now, if I added some cream right on one side, and oh, I do like cream. I shouldn't, Dennis says it's not good for me, but you can whip it around and then it would be a homogeneous. But at this time you add it in, and we like oat milk in our house, so you can have it on one side and not the other. That would be a heterogeneous mixture. So I think you get the idea. Good review. Heterogeneous mixture, homogeneous mixture. Now, if we do live in that ideal world where the millions upon millions upon millions of atoms that we're looking at in our hand are exactly the same, then you'd have a pure substance, and it would be what we call an elemental form, or metals usually is the term you'd think of as metals. They're going to be 100% iron or copper. A piece of copper is close to being a pure substance. Now, it's not actually pure because there's oxide layers usually on most metals, but the ideal is there, that the metallic form of your substances, the metallic form, it's the elemental form. Now, metals, or if it's a single element that's making up that metal, then we would say it's a metallic. That's the metal sort of side of the pure substance, the element. Or we can have the non-metals, and non-metals can do something that's kind of interesting. We can, and I apologize, there's two sides of the pure substances, elemental and compound. But in the elemental, you can be metallic, where it's all made up of, let's say, the mercury atom. But within the elemental, you can have, this what sometimes throws students off, I can still be on the elemental side of a pure substance, meaning there's only one type of atom. But instead of there being just one of those independent of the others, you can have what's called a diatomic elemental form of hydrogen. Diatomic meaning two atoms of hydrogen are bonded to each other, so it's still just hydrogen, but it's in a diatomic form. And that's exactly what happens with a lot of our gases, H2, O2, the non-metals we can have. They're still elemental, but they're kind of the non-metallic side. Again, now you need to put your notes into your my comments. You need to add yours just as I've added mine. You add your metallic and non-metallic. You may not have to add every single figure I add, but you're annotating your notes. So remember, elemental form can be metallic or non-metal. but it has to have the same atom. O2, 2 oxygens. H2, 2 hydrogens. It's still just hydrogen. And of course, if it's metallic, mercury, copper, whatever, they're sort of more like islands of the atoms interacting with each other, not in a diatomic form. Then last, we can have what's pure, like it's going to have pure distilled water. We can have a compound where it's 2 hydrogens and 1 oxygen makes water. That's its set ratio, and everything in there is just H2O. That's a compound. It has no impurities, no heavy metals, no microplastics. It's ideal again. It's maybe not achievable, but we're 99.999% water. That would be a compound form of a pure substance, which is matter. Remember those classifications coming on down the tree? Substance, mixture. 2 types of mixtures, 2 types of substances. And under element, we actually had 2 types of elements, the metals and the non-metal forms of elements, and then compounds. Now, I didn't get into the 2 types of compounds, but there actually are 2, and you just know that we're coming to see these later on. There's the ionic and covalent types of compounds. All right, move on. We're going to go pretty quick here just because you've seen in many of your high school science classes, you've seen some form of this description of substances, elements, mixtures. So remember, element composed of millions of the same atom. And what really kind of separates the talk of atoms versus elements is the size that you're at. In the introduction to the course, you learned, I hope, that there's macro scale side of science and there's the micro scale side of science. So what you can see, that's element. Your eye can see it. It's not an element unless you can see it. That's kind of the element size. But elements are made up of atoms, and you can't see atoms. That's the microscale side. So when we say atoms, we're thinking micro, and when we say element, hey, I saw that element is gold. Or sorry, I saw that the element was shiny. You can't say that an atom is shiny. You need a lot of them to be able to see them, to see that they're shiny. So this is kind of macro scale and micro scale. So we're going to just put that. We have the I'll put macro here so we can use this for something else. Macro and micro. But we can have, again, you remember the metallic types of elements, the metals, and we can have the non-metals. And we said those can be in the diatomic form, like H2, and we could have copper as a solid, where it's just, this would maybe be a gas, but they're still in the elemental form. Now, compound, they are composed of 2 or more atoms, different atoms. We're going to kind of point that out here. Chemically combined in a set ratio. So we have to have 2 different atoms to be a compound, or this can be a set ratio or fraction, I guess we could put there. So we have to have 1 to 2, 2 to 3, a ratio that's set. To be a compound, it can't just be a mixture that's random. Compounds have a set ratio of 2 different atoms. Now I'm saying different because when we say compound, you have to have at least 2 different atoms coming together. So I'm going to put that in here, 2 different atoms coming together. So let me give you an example of that. So the easiest one may be CO2. I have a carbon and I have 2 oxygens, 2 different atoms coming together in a set ratio. But molecule, so this little circle would be what we call a compound. But a molecule is like a bigger term. It's like a 4-legged creature. Not all dogs, not all 4-legged creatures are dogs, but all dogs are 4-legged creatures. So it's like a logic circle within a bigger logic circle. When you say, hey, show me a 4-legged creature, you can show a giraffe, an elephant, whatever. But if you say, show me a dog, well, it's a four-legged creature that's more specific. It's the same sort of relationship between compound and molecule. Molecule is any two or more atoms bonded together. And they didn't have to be different. So it can be, let me say it again, 2 or more atoms of anything. Same ones, different. So, of course, hydrogen gas, we've been talking about H2, would be a type of molecule And so would CO2. It's two or more atoms coming together. But H2 is not a compound. Why? Because that's more specific, like dogs with 4 legs. This is more specific. It has to be two different atoms coming together. We're going to talk about that a little bit in class. So remember, we can have molecules, the bigger circle, molecules, which absorbs in the smaller circle, compounds. Know the difference between those two terms, compound and molecule. I think what I'm going to do, for sake of time, I want you to bring this page to class, and we'll fill it in class, just kind of showing some examples of either the macro scale sort of picture we have for salt, NaCl, and the microscale picture. So I'm going to show these two pictures are going to be actually microscale. There's the macro scale. This is iodine crystals. This is mercury, I guess, quicksilver liquid. We can show what it would look like at the microscale level. So we'll do that in class. So bring that page not annotated. All right. A mixture is yes, we said two types, homogeneous and heterogeneous. Different marker here. A mixture, we said, is two or more substances that are mixed but not chemically combined. So we had the example of caffeine. We had a cup of, coffee, and I had caffeine as an organic molecule and water as a solvent, so to speak, that is used to give me this nice tasting brown water. There's some tannins that give it the color and all that, but that would be an example of a mixture. They're not chemically connected to each other. It's water with caffeine in it. It's like a party on a floor, a dance floor. You have people on it, but they're not combined to make new kinds of organisms. There's just people mixed together on the dance floor, but they could walk away and still be set, not torn apart and made into some new weird creature with 4 legs or whatever. So it's just they're separate, but they're mixed together. That's a mixture. We can say, again, heterogeneous spaghetti and water, or we can have homogeneous coffee. Spaghetti. I just tipped my coffee over. Okay, so we have mixtures, homogeneous, heterogeneous. You get the idea. And again, what we're going to use to discern between the two, which is kind of controversial, is what level do you set the heterogeneous nature? Because like milk has little micelles of fats. Well, if you were to get down on that sort of small level, nanoscale level, you could see it. But we're going to say eye level. If you can't see some difference by the eye, it's homogeneous. If you can see a difference in that substance in one section over another, one part of it looks different from another, then you'd say it's a heterogeneous mixture. I'm going to do the same thing. We're going to skip this just for sake of time. I'm going to use, I think, ionic liquids. I had a plan to use that for a story between heterogeneous mixture and homogeneous mixture. We'll wait till class. We're almost done. Just 2 more slides. You're doing great. You've annotated your notes. You maybe got your cup of coffee. I'm on minute 13 or whatever. Let's roll. So let's move from structure to energy. And this is hard. In high school, most folks don't touch on energy and matter and motion because it's just too difficult for students to maybe conceptualize. But I hope it's not. I hope it's in class. It's going to be something you have questions about that you can have answered. We can slow down, just look at it and try to figure it out. So temperature is an intensive property which measures energy. So intensive just means it's not based on the amount of stuff you have. So for example, I can have a thimble of 100 degrees of water and I can have a bathtub of 100 degrees of water. They're at the same temperature, but you know, of course, which one you'd want the terrorist to throw you into or expose you to. It'd be the thimble of water. But if you have boiling water in a bathtub, not a good idea to say, well, I'll choose the bathtub, even though they're at the same exact temperature. So it doesn't tell us how much of something we have. It's an intensive property, just the temperature of that thing. You don't know how much you have is such and such. Well, temperature is a measure of the average, we call sort of thermal or just random energy bouncing around kind of things. The average thermal energy of particles in a substance. So it's not a very usable form sometimes of energy when you just have some hot piece of metal with a lot of random motions of the atoms in that metal that's at a high temperature. So you kind of want to have a uniform flow of things. That's not what temperature is. It's just kind of that random thermal vibrations or whatever. So there's a good video we'll watch on that, and we'll see how temperature kind of correlates to motion. You have more motion, more motion, you're going to have a higher temperature generally. Now, we do need to know a little bit of math here. I need to get some new markers. Some of these are just going dead. So anything that's in Kelvin, we know it's higher than the Celsius. So if we say, for example, I'm going to go opposite here. Let's say we have 23 degrees Celsius. But if we ever want to know what Kelvin is, we always have to have an addition of 273.15 to be exact, but we're just going to say roughly. Anytime we have some Kelvin or Celsius value, say whatever X is, we add 273 to give us our Kelvin value. So if 23 Celsius is what we started with, then we would say, well, I'm just going to add 273, and I'll get my handy-dandy calculator out. And hopefully this video won't be more than 20 minutes, but we're going to say, okay, I'm going to add 23 plus the 273, and I get 296 Kelvin. And just note that as that, you don't use a superscript circle. You say 296 Kelvin is 23 degrees Celsius. Now we can go the opposite direction. So if we know we're given the Kelvin value, we can subtract 273 to get the Celsius value. And that's what we're having to do here. So it's a little bit of math, a little bit of algebra. You know this one, and you're hunting for C. So you're going to have to subtract 273. So just know the equation, C plus 273 equals Kelvin. All right. So if we take that 54.3 and we're going to subtract 273, we get minus 218.7, and I'm not going to worry about sig figs right now. I'm just going to say it's close to minus 218.7 Celsius. All right, so Kelvin equals our Celsius plus 273. Memorize that. We'll use it a lot in class. Last slide. It's a big one, important one. So we got about 3 minutes left to get to 20. So I'm going to spend about 2 minutes on this, because what students typically learn is that they know from solid to liquid to gas, you have to add energy. You have to put energy into it. What's interesting about phase changes is students don't often understand why when you go, let's say, from ice to water, ice cold, let's say ice to liquid here, form of H2O, the temperature doesn't change. The temperature does not change when you melt ice. You may not have known that or remembered that, but in hopefully grade school, middle school, high school, you learn that when you go from having a cube of ice to water, the temperature does not change until all the ice is completely dissolved. And then the temperature can increase. It's so cool to think of it in terms of what we call degrees of freedom. I mean, you're not nerding out on this, but hopefully maybe one or two of you do. So motions, you remember in the first video, are tied to vibration, translation, and rotation. Those are kind of the basic types of motions you have of atoms. So we can think of this ice vibrating, and we're getting at higher and higher and higher temperature. Let's say it goes from minus 23 Celsius to minus 10. We're getting close to zero. And when we get to zero, of course, that motion of the water molecules in the ice can start to cause it to come apart, to start to gain rotation, translational motions, where at one time it only had vibrations. But they get so intense, it uses some of that energy to dump into some buckets of motion you never had occupied of translational and rotational motions. It's so cool. So you can think of it like having a little hole in the side of this bucket where you've been adding energy into vibrations, but As soon as it hits a certain level, it kind of spills out into translational and into rotational. It can't get above this level or temperature until all the ice is melted, so that we can have that now completely melted ice cube. All buckets can rise in energy, because we just couldn't take the solid vibrations. We're going to think of this as solid vibrations. We had to keep dumping because it would break apart. And when it breaks apart, it finds new ways to move. And those new ways to move need energy. It's just not going to come from nowhere. The energy from the vibration of the solid gets dumped into those new buckets of rotation and translation in the liquid. And the liquid going to gas has the same sort of phenomenon, but in the one bucket, translational motion really gets bumped up quite a bit. You got to have molecules that are going from, 7 miles an hour to 500 miles an hour when you're going from liquid to gas, and they need to get that energy from somewhere. That increase in their motion translationally, by translation, they need to get it from somewhere. So they're going to draw it from the other buckets of vibrations that you have in the molecules as they're in the liquid state, and the rotations you have in the molecules in the liquid state as you vaporize. So we're going to use a term that's not, I think it's kind of confused with evaporation, but when you have a complete blob of water in a liquid form and some vaporization happens, gas is generated, you get a blob of that water leaving, and we call that vaporization of the phase of liquid water. When it got to 100 degrees, we vaporized it. We added a lot of that motion that was from the rotations and vibrations and translations, and we dumped a lot of it into the translational motion of the water molecules. So that's kind of a way to understand why temperature doesn't change when you melt, because you had to fill 2 new buckets that had no energy at all in the melting process. And then water has to have translational motion increase greatly, and they have to break bonds to do that. That's why water is such a high heat capacity. It's why it's used for cooling towers, because they can draw in a lot of heat, because that takes a lot of heat to go from liquid to gas. And the temperature doesn't change. It's still going to be 100 degrees until all the liquid is gone. Some terms you need to know. We're at 22 minutes. I apologize. I'll try to keep these short, but we're going to know sublimation, solid going directly to gas. We need to know deposition. That's gas going directly to solid. And then anything in between, melting and freezing, that's the liquid and solid relationship. Vaporization, please don't use evaporation. That's a term more like drying clothes out in the clothesline. But vaporization and condensation. And know kind of those 3 motions we had. We had vibrations within the solid, and that's all we had. Then the liquid, it filled up some 2 new buckets, not changing temperature. And then once we got to a fully liquid state, we could go from 0 all the way up to 100, and then we go through the next phase change, where a lot of energy, just remember, goes into the translational state for the water molecules as they go from liquid to gas. Hey, thanks. Sorry for this being a little bit long. Bye-bye.